Henry's law, right? Henry's law deals with the solubility of gases in liquids, right? And what does the law say? Law says that, you know what, the solubility of a gas in a liquid at a given temperature is directly proportional to the partial pressure of the gas present above the solution. Okay, so let's take a moment here. Let's read it again, right? Read it again. Let's try and understand, right? So let's read it twice or thrice, and then we will understand what this is trying to say, right? This is saying the solubility of a gas in a liquid, right? So the solubility of a gas in a liquid, the solubility of a gas in liquid, this is where it is pointing, right? Solubility inside, okay, is directly proportional to its partial pressure, of the gas present above the solution, right? Partial pressure of the gas. One second. Yeah, okay, cool. The partial pressure of the gas above the solution. See, it might be a bit confusing, right? What this is saying is, that, you have this cold drink here. Oh my god, that doesn't look like a cold drink at all. But yeah, let's say, you have a cold drink here, right? And let's say this is your bottle of cold drink, right? And so this is your cold drink here. This is saying and let's say this is closed, right? They're saying the partial pressure of CO2 here, right, is proportional to the solubility of CO2 inside the solution, right? It's saying above the solution, the partial pressure of CO2, or we can say, it's population density. Remember, try and understand, right? Correct, right? Partial pressure is essentially equals to what? Population density multiplied by RT, right? R is a constant at a given temperature they have already fixed. So R is a constant, temperature they have fixed already, right? So partial pressure is essentially proportional to N by V only, population density. What it is trying to say, then again, take a note. This is super important. A lot of students do mistakes here. Partial pressure of the gas above proportional to solubility inside, right? Try to form this, right? Partial pressure of the gas above the liquid surface proportional to solubility inside in the liquid, right? That's the relation here. Point is, what is partial pressure? Let's quickly deal with that as well. So the point is, if you have oxygen and nitrogen, right, let's say separately, and let's say they are applying 159 millimeters of Hg, and this is applying some 593. Anyway, these are weird numbers, don't focus on that. But the point is, if I contain both of these gases in a container, this container has a volume V, this container has a volume V, this container also has a volume V. So in this third container, both of these gases are contained, right? So both of these gases will be also colliding with the walls of the container, right? They will also be applying their separate pressures, right? So in the rightmost container, what you can say? You can say that, there is some pressure which is oxygen is applying, and there is some pressure which nitrogen is applying, right? So the total pressure is pressure of oxygen plus pressure of nitrogen, but their individual pressures are referred to as partial pressure, right? With that, let's sum it up, the Henry's law in the form of an equation, and it goes somewhat like this, right? Let's have a look at it. It's saying partial pressure, is equals to, some weird term is written. Okay, so let's put it board, right? Don't look at it. What I'm trying to say is that let's first read the labelings here. P is partial pressure of gas over the solution. This is some constant. X is mole fraction. What I'm trying to say is that the partial pressure of the gas, we are going to say CO2 for now because that helps us understand it better, right? Partial pressure of CO2 gas above the liquid, right? Above the liquid. Where is my bottle? Right? Yeah, there is my bottle. This doesn't look like a bottle. But yeah, the partial pressure of CO2 here, it should be small p, right? Okay, is proportional to, what should I say? It's proportional to solubility of the gas inside the solution, right? Inside the solution. Okay. So let's call that mole fraction, right? Mole fraction of the CO2 dissolved. And because of that constant we introduced, right, to get rid of this proportionality, to get an equality here, we introduced a constant here, and we called it that, you know what, this is equals to kh into mole fraction of CO2. Now why kh? Because of the h is because of the henries, right, and k is a constant symbol that we very popularly use. And so the mathematical expression turns out to be like this, right? Let's read the labelings again. We have P partial pressure of the gas over the solution, okay? Then Kh is the Henry's law constant. X here is the mole fraction of the gas in the solution. Read it carefully. What is this saying? Is the mole fraction of the gas in the solution, inside the solution, right? Inside the solution is what we are talking about. All right, so yeah, this is what we are. And now what we are going to do is we are going to put this into an equation. So think about it, right? So let's say we have an axis over here. We are, going to put this onto a graph, or we are going to plot it out. What we can say is that, partial pressure of the gas is Henry's constant multiplied by mole fraction inside the solution. And we're going to call this as x-axis. We're going to call this as y-axis. You might as well write this as y is equals to mx. Once we have that information, we can clearly see that we have a straight line here starting from the origin whose c is 0 and the slope is the constant, the Henry's constant here, right? And this is essentially what we have. Now, this is not that difficult, is it? Right? It's pretty basic if you think about it, right? How about we introduce some variety here, right? How about we say that, you know what, I'm going to have a graph, right? But I'm going to have, three different temperatures. So this is not like a single graph. Think about it. This is not a single graph. This is basically what these are, three graphs, right? And you have plotted them on top of each other, right? You have superimposed them. You have, plotted them on top of each other. This is not a single graph. This is three Henry's curves, right? Not curves, but yeah, three Henry's plots into one, right? Keep that in mind. Now the question is saying that, you know what? How about you compare KH and how about you compare temperature? Let me say about that, right? Let me talk about that here. So what does that mean? KH is a weird term, first of all, right? You should keep that in mind. So here we are keeping the gas same, right? We are also going to discuss what happens if the gas is different. Okay, fine. Okay. So in fact, you know what? Let's consider these two cases and let's handle it here only. Right. So let's say we have two cases. One is the gas is same and another is the gas is different. Right. Okay. So let's say you take the case of NH3, right? And let's say you take the case of CO2, right? Now we know that, and let's say the solvent for these both of these is water, right? Okay. Now the point is, we know that NH3 dissolves more. NH3 dissolves more, right? So the point is, we can say that what, in this formula P is equals to KH multiplied by mole fraction, we can say that for the same partial pressure of NH3 or CO2, right? The mole fraction of NH3 will be more. Think about it again. What did I say? What did I say? What did I say? Right? Okay, think about it. Partial pressure of NH3 will be equals to KH for NH3, right? Multiplied by mole fraction of NH3 inside the solution, right? Partial pressure of CO2, oh, that does not like CO at all, CO2, right? Will be the Henry's law constant for CO2 multiplied by its mole fraction. Now, my point here is, right, let's say for the same partial pressure, I'm asking for the same partial pressure, which one of the two gases which will have a higher solubility? So we know that NH3 has a higher dipole, higher polarity. In a polar solvent like water, NH3 will dissolve much more frequently, much more, possibly, right? There will be a higher solubility. Correct, right? Then, so my point is, if these white circles, right, if partial pressure of NH3 is the same as partial pressure of CO2, what we can easily say, is that for that condition, for their partial pressures to be the same, right, the solubility of NH3 will be more than the solubility of CO2. Yeah, that is very true based on the facts, right? Based on that, we can easily identify that, you know what, the Henry's law constant of NH3 and the Henry's law constant of CO2, which one will be greater? Think about it. Think about it. It's a very clear question. Let me provide you the framework. In these two equations here, the left hand side is same. In these two equations, the left hand side is same. So the right hand side in these two equations should also be numerically same, right? For that to happen, if you already know that the x of NH3 is more than the x of CO2, then you already know that this will be smaller and this will be larger. Why? Because XCO2 is small, so the stuff getting multiplied to it has to be larger numerically, right? So KH is larger. Get that point? You understand? So KH, yes, indeed, is dependent on the type of gas that you have taken, right? Right? Okay. So that's one thing. Another thing is that, let's keep the gas same, right? Let's keep the same gas, right? Okay, what is going to be in that particular scenario, right? If we keep the gas same, okay, so we have kept the gas same. Now what are we doing? We are varying the temperature, right? We are varying the temperature. Oh, okay. And let's say this is exothermic. Overall, the process of dissolution is exothermic, and because of that, if you increase the temperature, solubility decreases. Yeah, okay. Now try and study, right? Okay, let's say you're taking PCO2 is equals to KH of CO2 multiplied by mole fraction of CO2 inside the solution. Okay, now let's say for the same partial pressure, right, you're talking about the solubility at two different temperatures. Let's say temperature 2 is more than temperature 1, right? Let's say we are considering two possibilities, right? Temperature high, temperature low, same partial pressure, right? We are not varying partial pressure because we want to study the effect of temperature variance on solubility. So everything else has to be kept same. Yeah, and KH values. Yeah, okay. So we know that higher temperature is going to give us a lower solubility, right? A lower solubility. But the left hand side, the partial pressure is the same, that we designed it to be the same. So numerically, it should still remain the same, right? So if solubility decreases, KH over here increases, right? You get my point, right? If the solubility decreases, the KH increases so as to keep the partial pressure same. And that's why KH is also dependent on temperature, right? It is also then again dependent on temperature, right?